I'm pleased to present Wojciech Grabowski. Wojciech hardly needs an introduction, but I will give a short one. Wojciech is a former senior scientist transferred to emeritus just like a month ago, right? A couple weeks ago, in the dynamical and physical meteorology section of M-Cubed. He received his PhD in 1987 from the Institute of Geophysics in Warsaw, Poland. He came to NCAR in 1987 as an ASP postdoctoral fellow and was hired as a scientist one in M-Cubed in 1993. He's a fellow of the American Meteorological and Royal Meteorological Societies and is the recipient of several awards, including being named as a titular professor of physical sciences of the Republic of Poland. Wojciech's work spans a range of topics related to geophysical fluid dynamics, turbulence, and cloud physics. I'll turn it over to you.
All right, thanks, Joe. Yeah, Professor, it was nice to shake hands with President of Poland. I'm not sure if I would like to shake hands with our current president, but let's keep politics out of the seminar. Anyway, so yes, so I will be talking about some extra work that we've done together with Hugh and Kamal recently, and that follows my seminar almost exactly a year ago to the date that I will be referring to, as you will see. So, why we worry about droplet spectral width? Very simply, we know that it's important for radiative transfer, it's important for collision coalescence, especially gravitational collision coalescence. If droplets are of the same size, they fall with the same speed, they will never collide. But adiabatic spectral width is also important because we know that collision coalescence always typically starts in real clouds in almost adiabatic or adiabatic volume. So what happens in this adiabatic volume is actually quite important for collision coalescence. Now, looking at some observations, what we expect to see, to look at the observations. So this is fairly old paper with Jan Jensen. What is that? 25 plus 15, 40 years ago. 100 meters, 1 hertz data. I like this figure. It's from his paper, one of the figures which shows spectra at different cross sections, if you like, or passes through a cloud with adiabatic fraction close to 1 or close to 1 or 1. And this adiabatic width, or close to adiabatic width, is around 1 micron if you see. But if you do adiabatic parcel rising from the cloud base, it's only about 1.1 micron. And you will see that this is typical for adiabatic parcels. So that's a kind of a small cumuli. If you look for stratocumulus, that's my friend and colleague from University of Warsaw. This is the paper that we put together 2006 with higher resolution data, 10 hertz. The part of the figure taken from the paper looking at kind of a really relatively clean and then more polluted, higher droplet concentration, but still adiabatic fraction high, you can see that the spectral width at the bottom of this figure is a kind of between 1 and 2 microns, and with some, of course, spread when you fly through a cloud. So now, what is this eddy hopping idea? Or some people use, probably first was used stochastic condensation with Lianpeng Wang, my colleague from Delaware, now actually in Shenzhen in China. We coined this term of hopping eddies, droplets that hop turbulent eddies. The idea is, let's imagine you get a droplet at some height, and you get updraft, but it's also turbulence, which is shown by this kind of complicated trajectories. And we ask the question, if these droplets have different growth histories, can they be different in some height? So in kind of more general terms, you can say, well, what about, in general, turbulence affecting droplet growth? So you may remember, as I said, about a year ago, almost exactly to the date, a couple of days difference, I presented this seminar that basically asked the question, motivated by some people pointing this out in the literature, and I will show you who I have in mind. Why did we have it wrong? What was wrong with this kind of idea of eddy hopping? And this specifically refers to a couple papers that I can claim I was involved in starting this kind of idea and asking the question, can the small-scale turbulence explain the width of the droplet spectra and undiluted cloudy volumes? So this was basically Paul Vollencourt's PhD thesis that I was involved with late last century, but papers were published early this century. So the idea being that can we use DNS, the classical technique to look at turbulence, put some droplets in the flow and look what happens. Do they really develop some spectral widths if we start with the same size initially? So this is some example of those results. So those are droplets that grow by the diffusion of water vapor. So this volume is rising. And then we're looking what happens with droplet size distribution. So first of all, this is what fluid mechanics people pointed out, before us, of course, that if you get particles carried by the turbulent flow, they respond to the flow accelerations. And then this is what they refer to as preferential concentration. In other words, depending on the size of the droplet, that determines the inertia. The riser the droplet, the bigger the inertia. The particle turbulence interaction is basically the idea that droplets are ejected from regions of spinning air, if you like, in those vortex tubes that are typical feature of high Reynolds number turbulence. And you can see, for example, here, this is a kind of a tube. We're looking at the cross sections through the 3D simulation at particular moment. And you can see that there are no droplets in this volume. So larger droplets, you can see more easily this kind of a not random distribution of droplets, but droplets are basically responding to the flow, and droplets are smaller, they respond less. So, of course, the question is, if this volume rises and droplets grow, do they develop spectral widths? Initially, it's 0, and indeed they do. Now, here, the point is that this is really small volume. This is about 1 liter, so it's really volume like that. And simulation is run only for about 10 seconds, just because, 30 years ago, computers were not as big as they are today. So they grow, and there are some effects that you may expect, like there is no sedimentation. They really respond more to these flow fluctuations. If you include sedimentation, like in this solid line, then of course this is less. If there's no droplet inertia, of course the growth is slower because it's just kind of heterogeneous in the droplet distribution, but not really related to the flow. But nevertheless, there is some impact, and the question is, what would happen if you have larger domain? So I will not discuss other studies, but several studies after we kind of initiated that game started looking, and of course in DNS, the game is always larger domain, higher Reynolds numbers, so on and so forth. So the question is, can we really use these methodologies to look at the particle droplet diffusional growth? And in fact, that was pointed out a couple of years ago, and that's what kind of started, and I discussed it in more details about a year ago. Is there anything wrong with this approach that you get periodic domain and you have those droplets kind of moving around? And if you think about this, of course there is, because if you get infinite box and droplets are kind of moving with the turbulence, they will move out of the domain, whereas in this periodic domain, you kind of bring them back. You don't have to do it, but that's what usually you do when you get periodic box. It's the simplest approach, and you may ask the question, why this is a problem? Well, it is a problem because if you get droplets that start at some height inside the box, and one is moving up with some turbulent flow, the other is moving down, and of course, because it moves up, it grows. When it moves down, it evaporates. But then you apply these periodic boundary conditions, and they come back from the top, the small one, and the large one comes back from the bottom. So in a sense, once they are capable of circulating this domain, going up and down, but still leaving the domain and coming back. So that's, of course, a problem, because in reality, the turbulence provides a spreading of droplets, which this periodic domain doesn't include. To show that, in the paper that I just referred to, that is now in press, I'm using a very simple model to show that this really that is really a problem, which is a very simple model of stochastic condensation. There is no mean ascent, so you start with droplets at some height, and they kind of move around in turbulent flow. And turbulence is basically modeled with a very simple Langerer equation that describes the evolution of vertical velocity due to turbulent flow. So there is basically a history time, if you like, and kind of you force new velocity by depending on the TKE here and depending on what is the time scale of the turbulence here. So we used these two equations in the paper that we published 3 years back with my colleague from University of Warsaw. But we didn't look at the distribution of heights, how the height changes. So this is the new element, just to show that there's really a problem in this periodic domain approach. And in fact, there is a paper that came up with a scaling that you should expect doing this kind of a turbulent simulations. This is the square root of time scaling. And if you are familiar with turbulence and kind of work of Einstein and Smoluchowski, this type of scaling comes from basically dispersion of particles in the turbulent flow or in the diffusion in general. So if you start the simulations like many droplets, so initially 10 radius, so you can use the simplified droplet growth equation, and you use, let's say, 20,000 or 100,000 droplets, and you look what happens with the radii. If you calculate all of them, then it really, the size with time increases like a square root of time. So they were arguing that this is continuous growth of droplet size variance. Basically, they derive analytically that you expect to have that. But if you just keep those droplets that are initially within your box, disregard those that move away, then you can see that after some initial growth, then it doesn't grow anymore. So that's basically the problem that I discuss here, that this periodic domain causes you to miscalculate how this droplet spectra really evolves.
Wojciech, what if it's constant supersaturation with height? What if it's well measured?
Well, no, I don't know what will happen then, but your supersaturation is given here. So it responds to the velocity fluctuations, and it's being damped by the presence of other droplets. So the idea of having it constant really doesn't matter. The background can be constant if this is just vertical velocity. And I will show you that I'm using this towards the end. But this is just turbulent fluctuation. So initially, this box doesn't move. Droplets sit here, but the velocity fluctuations drive the supersaturation fluctuations, and then the droplets grow because of that. Okay, so those droplets that stay inside this box, they don't grow anymore. And those that move out continue growing. And to understand that, this is a very simple illustration. This is height, where droplets are. This is radius squared. Remember, we're thinking about this radius squared equation. So it's nice to think about radius squared rather than radius. So what happens, you can see that this is minute 2, minute 4. The later time, droplets move out. So this continuous increase in this figure, it comes from the fact that droplets move high or move down, and the spectral widths, if you calculate all of them, continuously growing because they just spread. But if you look at this inset, so this is basically 100 meters, so this is minus L half plus L half, all those droplets here kind of don't change in time because droplets move out, but those that are here are kind of the same. So this line represents basically this saturation, if you like, within this box. Now, of course, what you can do here, you can ask, okay, if we know that this slope represents the growth because of the dispersion, can you just kind of look only near the zero here and actually scale all the droplets back to this height and see what is the actual spectral width here? So you can do this, and this is the outcome. Depending on this scale L, that kind of determines the size of your box, if you like, and of course it affects turbulence as well, you can see that basically it's kind of saturates for the reasons that I will not discuss, but there is a good physical reason why it should saturate for large L, but it's very small. Look at the numbers. It's 1/100th of the micron, so it's tiny, even compared to the adiabatic parcel, okay? So you may ask the question, so is that really relevant to what's seen in clouds? Okay, so I started with a figure like that, arguing that you have droplets, they grow or evaporate if they go down, and this has been done before by Bartlett and Jonas, and I show it in my paper, but also others. The point is that I calculate kind of forward trajectories, if you like. I start at some level with droplets and calculate forward how they grow. And is that really the way to look at the cloud observations? I would argue not really, because what you see when the aircraft flies through a cloud, you see droplets, and you may ask the question, what happens if you go back in time? So rather than forward trajectories, you should actually consider backward trajectories from the height that the aircraft flies. So now we come to this part. This is really a new part. If you remember the old seminar, okay, so that was a refresher, if you like. But now we're looking at the simulations that will try to get it right, how we can do it. Well, I already suggested that this is how it was done by Sonia Lasser-Trapp about 20 years ago. I think Charlie was involved with her work. Charlie, is that correct? No? Al Cooper was for sure, but whether you... Anyway, so now, ask the question, the following question. So what happens when you select a point inside the cloud and look at those backward trajectories at different moments? So the cloud at 2 minutes looks like that. Those are trajectories for starting at 10 minutes and going down. So this is kind of the approach you want to have. However, that paper used a very elaborate approach to calculate those trajectories because the model was bulk, and then they pick up the point and they run back trajectories of given the flow, and then they bring microphysics along those trajectories. So it was really cumbersome. Well, if we use Lagrangian microphysics, we really don't need to do it, because Lagrangian microphysics, if you don't know what Lagrangian microphysics is, I can ask the question, where have you been over the last 15 or 10 years, let's say? But anyway, this is the trend that we're pushing because it has real advantages of looking at the particle-based Lagrangian approach. So whatever you missed in this previous study, you can do with Lagrangian model. And this is just a small slide that we put together in a Bum's paper a few years back to explain what Lagrangian microphysics is, with the idea that you follow individual particles, but we call them superparticles or super droplets because each of them represents many. But you need to have really high resolution to do those simulations, to represent turbulence in the right way, if you like. And recently, such simulations have been completed with the project that Kamal Chandrakar, who is unfortunately not here, he is with his family in India. That was kind of within the CAMPEX 2 project. I will be looking at the non-precipitating cloud. This is a visualization produced by sizzle with the rain falling out. There is a little bit of shear, that's why the cloud kind of leans. Shear in this direction. This is really, really high resolution. It's 12 by 12 by 11 kilometers with 7.5 meters. So it's really, I would say, unprecedented simulation, especially having billions of those particles, only 64 per grid box. So you may say it's not enough, not large enough, yes. But altogether, this is what we could have afforded. And then this shows basically the spectra that we have. So for those of you that are not familiar with Lagrangian microphysics, the idea is that you fill domain with those computational particles, super droplets. You sample the CCN distribution, and then if there is updraft that carries it across the cloud base, those particles get activated and become cloud droplets. So in this talk, I will be looking at the relatively small part of a cloud below the cloud base, across the cloud base, about 1 cubic kilometer. And the reason why I want to do that, because then I can be sure that this volume is adiabatic. There is basically no entrainment because we are far away from edges. It's only flow across the cloud base. And those are, so this is the cut through a cloud along the shear, cut along the shear. And this is perpendicular, so it's basically the same cloud, but because you cut it somewhere here, it kind of looks shallower because it leans. But this is the volume that I will be looking at. Now, if you would like to understand what's going on at the cloud base, this is a distribution of the vertical velocity at the cloud base. It's actually not the distribution of vertical velocity, but the perturbation. So I subtracted about 4 meters a second because otherwise you would have a lot of contours. The point here is that on this side of the cloud, there's stronger updraft, and on the other side is the weaker updraft. But you may say, how do you know that this is turbulent? Looks turbulent, whatever turbulence means, but how do you know that it's turbulent? Well, if you do spectral analysis, then this cloud is turbulent because it carries turbulence from the boundary layer. So I have to say a little bit how it is really forced. So it is forced in a way that we actually showed it a couple times already in previous seminars. Myself and Kamal had a talk, I remember. The idea being that you have basically a heating from the below that develops convective boundary layer, so turbulence is there, and at some point this kind of a homogeneous horizontally with some noise added flux, to it, you add a flux that has kind of a Gaussian distribution in the center of the domain. That forces a more coherent updraft that basically brings cloud to the existence. So the cloud forms because of this coherent updraft, but this updraft carries turbulence. And you may say, okay, this kind of looks like turbulent flow, if you like. Of course, it's not periodic just because the domain is periodic, but we're looking just at a small fraction here. So this would tell you that you really have a nice turbulence with kind of at least couple decades of turbulent eddies, if you like. So the point is that the cloud base is really filled with turbulence to begin with. It's not smooth. And the point is that you need to have high resolution to really be able to simulate that, okay? Now, so we're getting into some results. So this is this plot that I showed before. Those are plots that show the picture. Now, if you look at the updraft speed as a function of height, from about a few hundred meters, couple hundred meters, 500 meters, this is about the cloud base. So you can see that this, on average, this updraft accelerates. That's not surprising because you get, of course, buoyancy released near the cloud base, and then the updraft accelerates. But there is a lot of variability, and which actually it's shown in this picture. You may ask the question how you can define turbulence, and we will discuss this in a moment, but so that's this middle one. But first, let's look at the supersaturation profile. So, okay, I have to say that these lines are basically 5th to 95th percentile. This is the median, and this is 25 to 75. So this gives you kind of a feeling of the distribution across the cloud base at any given height. This is just the cloud base, so let's say somewhere here. So the mean is about, not quite, but close to 4 meters a second, and then those are perturbations from the mean. Now, supersaturation increases, supersaturation fluctuation, the mean or median increases as you approach the cloud base with large fluctuations, obviously, because of those velocity fluctuations. Then you get this classical maximum near the cloud base of maybe 0.5%, and then it kind of decreases and fluctuations decrease as well. That's because droplets are growing. So if you remember the supersaturation equation a few slides back, you get the forcing terms with vertical velocity and the damping term because of the droplets that grow. So that's why these fluctuations get smaller. Okay, so now this plot, so the question is how you really can define turbulence. Well, one way that we would like to do it is to calculate or derive or get from subgrid scale scheme the KE dissipation rate. So this is really not what model is doing. This is what subgrid scale are telling us what is the dissipation rate. And again, this is the median and the distributions, as I said before. As you can see, the median is kind of between 10 and 20. That's not atypical for, if you think about convective clouds, relatively gentle, I would say, convective clouds from the boundary layer. That value actually makes sense. Now, if you would like to know about microphysics, there is a small problem because if you use just the regular data, so this is basically the grid box by grid box data, if you like, and this is a little bit average data over 3 boxes in each direction. So first of all, this is droplet number, mixing ratio, droplet radius, and spectral width. So why this relatively wide distribution gets more squeeze, we understand that. That is because the technique has a limitation of small or relatively small number of super droplets, only 64 on average per grid box. So if this is purely fluctuating fields, then the standard deviation of that gives you the width of the distribution. So if you get few droplets, then the width will be relatively large. If you get more, that's get narrow. The good thing is that there is really no much trend in terms of median. So the median is not affected. Droplet size is not affected. And also, perhaps most importantly, the spectral width is also not terribly affected. There is perhaps some trend, but you can use original data and look at the spectral width. And as you can already see, the spectral width is much larger than just 0.1 micron as in those initial slides that I show you. So just a couple examples how those spectra look like, depending on how many droplets you use. This is 70, this is more, this is even more, and the spectral width is, this is close to 0.5, this is a quarter, this is 0.42. So definitely not very narrow. If you look at this data, just fly an aircraft horizontally, this is what you would see. The mean radius slightly increases as you fly through a cloud, if you like. That makes sense because the maximum updraft is on this side. So maximum updraft, the stronger updraft means more droplets activated, means smaller radius. So this gentle slope, that makes sense. This is spectral width, and it kind of varies if you fly, goes to few tenths of a micron to maybe 1 micron. If you actually look in the vertical, this is what you get. So basically cut here, you activate, they grow. The spectral width is kind of depending what you look like. This is just purely randomly selected. I promise you, I didn't kind of look very strongly to find, this over micron width. But anyway, this is what you get. Now, you may then ask the question, okay, so this is what the 3D model gives you. Can we understand that? So let's take the updraft and then take adiabatic parcels. You know what adiabatic parcel is. You take the volume, it rises, supersaturation reaches maximum, you activate droplets. What is the spectral width and what is the radius if you move that parcel up? So the droplets are growing. Spectral width, as you can see, it's relatively small. It's between 0.1 and 0.2. If you look at the scale here, 0.1 and 0.2 microns. So those are really, really narrow spectra. Okay. Now, if you compare that side by side with the spectral width from the model, you can see that there is indeed some impact of turbulence, because there is no turbulence here, 0.1, 0.2. This is 0.1, 0.2, up to several tenths of microns. So there is something that goes on that perhaps this eddy hopping, the fact that this cloud is turbulent, makes a difference. Now, there is another effect that you may ask me, okay, what about these different vertical velocities at the cloud base? Because here you get updrafts, parcels rising with different updrafts, actually slight different profiles of the updraft. They still don't represent that. But what about if you have those parcels and you move up and you mix them? Well, why that should be important? Well, that figure kind of explains it, because imagine this is the parcel that has smaller radius. In other words, produces higher droplet concentration, smaller radius. This is another parcel that has smaller mean radius, which means lower droplet concentration, larger radius, smaller droplet concentration. When you mix them, then obviously you don't only get much wider spectra, but you can get the bimodal spectra, for example. So let's do the exercise. Let's take a couple of those parcels, for example, the narrow, the smallest one, the more, and you mix them. Can you explain that? So this is the outcome of this such a very simple procedure, mixing with different proportions. And you can see that, yeah, indeed, if you look here, it's 0.1, 0.2. This is 0.2, close to 0.3. So yes, there is some impact of that, but probably not sufficient to explain those large droplet spectra. So the answer is that the mixing between these parcels, yes, it has some effect, but it's probably not strong enough to explain this effect. Now, of course, okay, so this is what model is giving us, but besides just saying, okay, this is nature, we would like to understand what actually comes, what are those differences come from, what is the impact, okay? So this is what I've done. I develop a very simple system that is one-dimensional, so it's Eulerian flow with Lagrangian superdroplets. And that's the mechanism, that's the tool that I'm trying to use to understand this broadening, if you like. So the motivation actually comes from an old paper that you may know some of the authors, or maybe you know all the authors, that Terry Clark and Bill Hall wrote together in the 70s, basically looking at the three-dimensional simulation of a turbulent flow inside the mean ascent, if you like. So it's like, and they actually were arguing, and they are right, that this is relevant to this droplet broadening, that this is basically stochastic condensation that they simulate. So I can do that, but I decided to do something simpler. That I decided to do a one-dimensional representation of this. So basically, you get a one-dimensional column, if you like. So it's one-dimensional. The reason why I plot it as a two-dimensional is that I would like to show those droplets that are there, and they are carried by this mean ascent. So the thermodynamics is very simple, water vapor and temperature. So you get basically advection in the vertical, and then you get condensation. So inside each grid box, you have droplets that move with the mean ascent, and condensation of those droplets provides latent heating and produce their growths. And of course, you start somewhere below the cloud base, So droplets, let's say 95% humidity or something like that. So droplets, first they grow, they activate, and they continue growing. So I use the same CCN distribution as before. And this is just the illustration why the super droplet approach is important, because if you would like to do it with bin microphysics, that's the problem, because this equilibrium supersaturation depends on the droplet size. Basically, the larger it is, the closer it gets to zero. We know that, so that's kind of a cloud microphysics one-on-one, if you like. But at the same time, it also depends on what is the CCN, this soluble particle that is dissolved inside the droplet. If it's very small, then of course that peak is the activation. So this difference is important when droplets are approaching activation. So if you use this system, there is no turbulence yet. This is just a smooth channel, and droplets that leave from the top, I move them back. So the number of droplets is basically given, and of course I move them, but I change their size to size of the droplets that are here. So kind of almost like dry CCN. So there is no turbulence. So, okay, so it's 1 kilometer domain. There is 100 grid points. I use constant updraft. Okay, you may say, well, the updraft increases. I don't have results. I have a code ready to actually simulate increasing updraft, but not yet. So I use 2, 3.5, and 5 meters a second, constant ascent, 10 meter grid lengths, 1/10 of a second time step, and it's substepping for droplet growth. You don't need to know all these details. For advection is pure MP data. Inflow is kept constant, and outflow is unimportant. Whatever leaves the domain on the top doesn't really matter. We don't consider what happens above our 1D box. Now, super droplets, I look at this CCN, and I use 100 bins on the logarithmic scale from 2 to 200 nanometers. If actually you would be careful to look at those, the concentration here so low, here so low, really what matters is this part. So altogether I have 640,000 superparticles. Initially I randomly distribute it inside each column, and initial radius is given by the equilibrium with local supersaturation. Those are kind of things that you would do, nothing special there. They are advected with the mean updraft. And then, as I said already, when they leave on top, you bring them back to the bottom. And perhaps important point that I don't consider subgrid scale supersaturation variability, if you like, within this 1D non-turbulent column. All droplets, all super droplets within one grid volume grow with the same in the same supersaturation. So there is no interpolation to droplet position, nothing like that. I don't think that's really important to consider. So all of them inside the box grow with the same supersaturation. Okay, so as I said, no turbulence yet. So what are the results? Droplet number mixing ratio, mean radius, spectral width, and I'm showing here the adiabatic parcel. So as you can see, as you might expect, because there is no turbulence, the spectral width kind of is similar to what is inside the adiabatic parcel. The spectral width is between 0.1 and 0.2 micron. It's kind of here, okay? And 3D model gives you something like that. So at that point, it's just that this 1D model compares with parsers. There are some differences because those parsers are actually moving with some profile. Here, there is no profile, just constant values. But the comparison kind of looks good in my opinion. Now, here, what is really interesting is how to bring turbulence into this picture. So the temperature and moisture equations don't change. The condensation rate doesn't change. Basically, all the droplets within the box provide the condensation rate. Now, the trick here is to actually grow droplets, not only by the mean supersaturation, and then this is this equilibrium supersaturation, but actually at the supersaturation fluctuations. Like in my paper with Gustavo, of course, droplets will move, will be affected by the velocity fluctuations. Now, velocity fluctuations will be done or are done with this Langevin equation or solution of the Langevin equation for the vertical velocity, basically mimicking the effects of turbulence. And the supersaturation is basically, this is the response of the vertical velocity fluctuations, and this is forcing, and they are being damped by other droplets that are in this box, with the phase relaxation time. So there are some parameters that need to be put into this model, like some time scales here and the phase relaxation time. But before I do that, a kind of quick in-word summary. So when I add turbulence, each super droplet in the grows in the supersaturation that comes from the combination of the mean supersaturation, as in this case without turbulence, and fluctuating supersaturation that is driven by the stochastic model. And stochastic model parameters are derived from 3D simulations. So first of all, what I'm using is this TKE dissipation rate that I pointed before, and I will show you a picture in a moment, for those different updrafts from the cloud-based data that I have from 3D model. Now, this integral length scale comes from basically analysis that I think you did, Hugh, or Kamal did, and they gave me the number. Use 300 meters. Okay, 300 meters. I asked Peter in the turbulent boundary layer, what should I take? He said, oh, depth of the boundary layer. Well, it's kind of a large number, a kilometer, or maybe even more. I don't want to do it. I like kind of smaller numbers. So that's what I took. And then the phase relaxation time is basically the same for all super droplets within the box, and it comes from this 1D simulation without turbulence. I will show this in a moment. And then, you know, the TKE that actually drives velocity fluctuations comes from the length scale and the dissipation, and this integral time scale for the turbulence comes from the TKE and the length scale. So those are parameters that I have. Now, some arguments. So this is at the cloud base. So this is you've seen this picture before. So this is the kind of a distribution of the updraft. So here's the updraft velocity. Here's dissipation rate. That comes from the turbulence scheme. So it's really not the dissipation rate, but it's something that I kind of think, and again, I consulted with Peter. Peter said, okay, that makes sense if you do that. So this is what I did. And those points, basically you can see that depending on the updraft, the dissipation rate changes. So I included that. I checked my code several times. I still don't know whether this dot is here. I would like this dot to be lower. You can say that probably it's okay to put it down, but anyway, so this dot comes from averaging 1 meter around this 2 meters, and then 1 meter. If I do averaging by half a meter, so 25, 25, I get basically the same value. So I don't know what's the problem with this figure, except that I'm only showing 20% of data points. So maybe there are some points which have higher value that basically offset this up. But anyway, this is what I took for the model. This is the phase relaxation time. So for different updrafts, constant updrafts in this 1D simulation, this is what you expect. That, you know, if droplets are not activated, the phase relaxation time is large, hundreds of seconds, if you like. But then it really decreases after activation because this is fairly polluted environment to something kind of close to 1 second, which makes sense. So this comes into the model. Now, what about model results? So again, mixing ratio, mean radius, and spectral width. So maybe I go immediately to the picture that shows the difference from the without turbulence. So one thing that you see, first of all, where are those wiggles? Well, because this is turbulence, so the number of droplets in a box kind of varies. So that's why those fluctuations come from. Now, of course, you can see that the turbulence brings the difference between this adiabatic parcel without turbulence, no, not parcel, I shouldn't say that. The adiabatic stream, if you like, updraft, adiabatic updraft, and you may ask where this comes from. Well, it comes because you activate and you may deactivate because of supersaturation fluctuations. Droplet radius, there is this peculiar thing here that actually activation and deactivation of those particles. And the most interesting part is, of course, here. Without turbulence, it was 0.1, 0.2 micron. Look here, I'm getting values above 1 micron. So this is close to 1 micron. This is over 1 micron. Look, this is the scale. There is some impact. So just to show you some example of spectra, how I'm doing on time. I need to kind of do faster. So this is without turbulence. You can see the radius is 8.7 micron, spectral width is 0.1 micron. This is with turbulence with 2 meters, turbulence with 5 meters, 10 microns, 1/1 micron, and 0.8 microns, 0.6 micron. And you can see that those are kind of much wider spectra. So of course you may ask the question where those differences come from. So I already alluded to that when you get turbulence, you get fluctuating supersaturation that allows cycles of activation and deactivation. Without turbulence, a droplet is activated and then it grows. Nothing can happen. But with turbulence, you can activate or not, or if you activate, you can deactivate later. And what is, in my mind, very important is that activation height varies among droplets. And this is, those figures kind of illustrate that. So those are height versus, as a wet radius as a function of height for droplets of different dry CCN. So this is very small CCN, 10 nanometers. The dashed line is the critical supersaturation. This guy just grows in the updraft, never reaches the critical supersaturation and stays as a non-activated, how you call those particles? Say? Haze, yeah. So this is just stays as a haze particle. So now we're looking at 20 microns. Look at that. At 20 nanometers. There are three, in each of these plots, there are three, just randomly selected three droplets. You can see that some of them activate and then grow into droplets, but one of them doesn't actually activates and then deactivates. Now, the important point here is that this activation happens over some depth. It's like maybe 50 meters here, but depending when they activate, they grow into different sizes. Now, this 90 nanometers, all of them activate, but because they activate at different heights, higher up, they already different in size. So the small difference here makes some difference a lot, and that's where this spreading comes from. So this is one example. This is one reason. Now, the droplet growth depends on this difference between supersaturation and equilibrium supersaturation, which is shown here. Is that important for the growth after activation? How you can look into that? Well, imagine you do a test simulation in which droplet, the equation of growth before they activate is exactly like before, but once they activate, you switch to the simplified droplet growth equation. In other words, after activation, you don't consider the equilibrium supersaturation in the growth. So, in fact, the fact that you consider equilibrium supersaturation makes the growth irreversible, and people actually studied that. If you go up and go down, that makes a difference on the growth and evaporation. It's irreversible because of this. So Alexei Korolev, I think, had a paper on that, and more recent people from PyChamber had a paper on that. But anyway, so the idea is what impact that gives. And this is the answer of one of the simulations, this 3.5 meter, this in the middle. No turbulence, 0.1 micron spectral width. With turbulence, 0.76. Now, if you does do what I just explained, that supersaturation, this equilibrium supersaturation is set to 0 after activation, you still get significantly larger spectral widths. And of course, you can argue that this is just the difference because you activate at different heights, okay? Now, a small point, but perhaps important, is that if you would like to do this study using bin microphysics, then you will not be able to do it. Reason? Bin microphysics doesn't consider those effects that I'm talking about, unless you do something really like two-dimensional bin microphysics, for example, or you do only one size of CCN. Once you get a spectrum, it's important to keep track of what's going on inside the droplets in terms of what is diluted. And Lagrangian microphysics does it, bin microphysics, the simple bin microphysics doesn't do it. All right, so we are at the end, so some summary. A lot of words, but I put some pictures. So the words, the picture is worth 1,000 words. There's no 1,000 words on this page, but there are some words. So understanding adiabatic droplet spectral broadening in turbulent environments attracted significant attention of turbulence community in recent decades. I can say decades because from it's a couple decades at least. So DNS, direct numerical simulation, an approach that we kind of invented with Lois Thomas that she visited here. We called it scaled-up DNS, that you make the domain larger, but then the Kolmogorov scale is larger as well. So we call it scaled-up DNS. But also a stochastic model have been used to show that the impact of turbulence in undiluted cloudy volumes on the adiabatic diffusional spectral growth. However, those idealized studies feature a fundamental flaw of periodic domains that allow droplets to circulate in the vertical. If droplet vertical spread is considered, then spectral widths saturate at small values. And you remember you discussed this figure that all droplets continue growing. There is this square root of time scaling, but if you just look at droplets that remain inside the box, it really saturates. Now, analysis of realistic high-resolution cloud simulations, the grid length about 10 meters, applying Lagrangian particle-based microphysics demonstrates a significant impact of turbulence on the adiabatic droplet spectral in a simulated cloud. So this is the figure. And to understand the impact, a simplified 1D Eulerian Lagrangian model of a vertical air current is developed, motivated by where Terry and Bill did some 30 years ago or more. Without turbulence, narrow droplet spectra agree with results from adiabatic parcel, including the impact of turbulence of droplet growth. This kind of eddy hopping idea results in the adiabatic spectral width even larger than the simulated by the three-cloud model. You may ask why the larger? The answer is I don't know, but I certainly would like to understand why. But the kind of the bottom line of all this work is that droplets hopping turbulent eddies can explain increased spectral widths in adiabatic cloud volumes as seen in cloud, in situ cloud observations. So that's kind of like the bottom line of this work. Thank you very much.
Okay, questions? Let's go to Roy first.
Yeah, in your final statement there, you said droplets hopping turbulent eddies can explain increased spectral width. One area in cloud physics that we've been wondering about is why we get broader cloud droplet spectra in Hawaii. And one of the answers has been giant nuclei, going back to, I think, Woodcock back in whatever.
Yeah. 50-something.
Does this speak to that, address that question?
No, I don't think so, but that addresses just one of the ways you can broaden them. And of course, if you change CCN, then of course those numbers that I show will change. So the kind of cleaner environment, larger droplets will have larger spectral widths. But if you bring things like giant or CCN, that will change the specific numbers that
There is a giant CCN mode in this as well, though. You do have a giant CCN mode.
well, I wouldn't call it but it's still
It's
like
small. It's a small concentration.
it's small concentration, but its effects probably that what Kamal showed. It affects the collision coalescence, although not to the level that we would like to see. But that's when you may argue the collision coalescence because you produce larger droplets just by they may never activate because for some of those giant CCN, the activation radius may be like 30 microns. They never get to this size, but they behave like real droplets, and they're already bigger than other droplets. So yes, not considered. Well, they are, but they are in such a, I have it somewhere, in such a small concentration, couple orders, at least magnitude difference. So for the spectral weight, it's probably very minimal impact. Yeah.
Yeah, that was my point.
Yeah.
Yes, in 2011, we conducted an experiment on deep convective clouds based out of St. Croix Virgin Islands with the C-130. And what I had them do was, because I was interested in exactly the questions you're asking, that we had them make a constant altitude penetration below cloud base, and CCN were measured, and then we had them step up in 100 meters. And I looked at entrainment, but this would be a really good, because we had every measurement, plus turbulence at 15-meter scales.
Well, send me the data. I can run the model. I don't think we can run. I don't think we can run ASD simulation, or Kamal can run with that resolution. He can run.
But
with,
that's, those data are available, and I looked at entrainment.
Is it published? Send me
we
the paper.
publish a number of studies on it.
Yeah, so
looked
send
at
me.
entrainment, but this would be a really good study to look at broadening, because we had excellent particle size distribution measurements, cloud droplets.
Yeah,
of
yeah.
course.
We can add it to the paper. It's not too late. Paper is in review. Peter.
I was curious about those two figures at the top there.
Yeah.
You've based it all on one single snapshot in the red box?
Yeah.
That surely isn't representative of the turbulence that's there. I mean, a few seconds later, a few minutes later, that's going to be very different.
But that's a you may say Taylor hypothesis. Am I right? In action, if you like. We can look at the data, whatever, 30 seconds or 1 minute later. I don't think the picture will
Yeah, I've
change.
done that. The statistics don't change that much.
Yeah.
In fact, I would say it's, especially near cloud base, it's kind of surprisingly constant in time. Whereas the upper part of the cloud really kind of develops
because
and that kind of thing. But near cloud base, it's relatively steady once the cloud
but
forms.
if you look at this plot, look how the spectral, which, I mean, here it's, let's say, around 1. But look higher up, and that, of course, the effect of entrainment, mixing, and maybe even collision coalescence. So that's above my pay grade. I don't want to look here. Let Kamal is young, so he can look at that.
Trained clouds.
I like this one because this is, and we've been doing those DNS studies for decades, I can say, arguing that this is relevant to clouds. We were doing this DNS box that is rising, of course, no entrainment. So those studies, we were thinking is relevant to this, but of course.
Yeah. So the spread in the second figure from the, I was curious whether that's a time-dependent phenomena or it's really typical.
So I think Hugh already answered that doesn't change us inside this box that much.
Yeah, for question about the updated eddy hopping model, I was wondering, did you consider the sedimentation effect or the gravity that affect the terminal velocity of different size of drops?
Yeah.
Since you've derived the height-dependent size and it increase with height,
Yeah.
does the sedimentation counteract these height-dependent?
So let me answer this way. I ran simulation with my model, including, that was Kamal's question early on, and I ran, it's virtually no difference. And it kind of makes sense by looking at the scales of, let's say, 10 meters. Maybe if I go to higher resolution in the vertical, maybe that will be some impact. But sedimentation, I mean, those droplets fall, 10 micron droplets fall 1 centimeter a second. So to make it a meter, it needs 100 seconds. To make 10 meters, it needs 1,000 seconds. And those simulations that I run are typically like a couple thousand seconds. So, there's always, I mean, in the pi chamber, when everything happens within 1 meter, yes, that is important. But here,
Yeah, maybe not in this real case, but in your parcel model that you proposed earlier, where you derived the height-dependent R, where you see larger R in the higher up than in the lower.
Sorry, I wanted to show the picture, but I cannot. It's frozen, so no picture.
Yeah, just I wonder if it's possible to run another model where you consider the trajectory of particle that including the impact of gravity. Then you form a new relationship of the size distribution with height, and whether this will change the picture when you consider the sedimentation.
Well, I've run those simulations without. At scales that I'm looking at, probably, I would argue probably not. At pi chamber, yes, there may be some answer.
I think the other key is these drops are really small. I mean, look at the scale down there. The biggest ones are like, what, 15 microns or something? 16 microns.
There is a question on the...
Yep, so we'll have a question on Slido. Does proximity to other droplets influence local supersaturation and droplet growth?
Not in my model, because the phase relaxation time comes from the flow without turbulence. But I would argue, yes, it does at very small scales. If I go back to one of the initial slides with this 1 liter box, that of course locally droplet concentration changes. But these droplets are rearranged on very fast time scale, maybe a second, because turbulence carries them from one place to another. That was actually one of the arguments that Paul Vollenkut has in the paper, that the effect is relatively small because droplets rearrange themselves very quickly. So in the model, it's not there, but I would argue there's actually a comment on that in the paper, that those effects, those very small effects, these preferential concentration effects, we had this discussion 30 years ago or 25 years ago with Raymond Schoch, who was arguing that this preferential concentration is so important. And I was saying, I don't think so. Because if you look at the snapshot, yes, but you look at the snapshot 5 seconds later and these droplets are in completely different place, so they experience different environments, if you like. So yes, maybe for collision coalescence, mostly because collision coalescence is irreversible. So when the droplets collide, it's done. But not for condensation, I would argue.
Okay, I think we should probably wrap up. You can go talk to Wojciech afterwards because we're running about 5 minutes late. So let's thank Wojciech one more time.
Thank you. And I promise this is not the last seminar that I will give.